Okay. So this is the problem review session for the um math counts team selection round. Uh, wait, never mind. So I'll be going over problems number 10, 14, 15, 16, 17, 18, 19, and 20. If there's any questions about any other question from um before 20, you can ask me in the chat, or you can uh contact me later. But okay. So uh okay. So um there's no questions, right? So I'll get started by getting number 20. Um so okay. So here's number 20. If it will let me paste. Okay, so here's number 20. We can have a quick look at the problem. Um, so it says we have a region enclosed by this equation that has absolute values in it with the inequality less than 12. And we want to represent this in the a radical form like this, and then find a plus b and a plus b plus c. So the first thing here is to try to draw a graph of this. And we can oh, okay, that's right. Okay, so we can draw our coordinate plane like this. So um and so let's try to graph this equation. So it's something that is a good technique to graph these equations is to first ignore the absolute value and graph it in the first quadrant. So we can recognize this um as the equation of a circle uh with center 3, 3, and radius 12. And radius root 12. And that will look something like this. Um, and then we can sort of reflect it to the other quadrants, and we can get a similar graph. So, I'm going to look at graph here. So, shoot. Uh, do I try again? Okay. Evidently, it's- okay. So here's a graph of the equation. And so what we're trying to find here is the region we're trying to do less than. So I draw um okay, here we go. Uh so we're trying to find this region here enclosed by these four like roundish shapes outside of this diamond and inside this circle. All right, so we can first split this into many regions in order to make this easier. So we can cut it here as well as here. Um right, so let's as well as here. And we can see that this region over here is 1/8 of the entire region. Um, and so now we just need to calculate this. So first we can draw more lines to connect the center with the points that are on the x-axis like this. And so we now have two different parts. We have the part that is inside the triangle and the part that isn't. So the part that isn't inside the triangle or outside of the triangle can consist is just a circle or part of a circle. So it's root 12, which is the radius squared, times pi times 1/3, since we can see this part takes up 1/6 of the circle, and this is 1/2 of the circle, so the rest is 1/3. In order to see that that takes up 1/6 of the circle, uh what? Okay. Let's try to calculate some of the values of the lines. Okay, that's interesting. Um, so if we drop an altitude from here, we find that this part here is root 12, right? And this height is 3. So we have this length here is 3 root 3 by Pythagorean theorem. And then at this point, we can recognize this triangle as a 30, 60, 90 triangle and conclude that this angle up here at the top, this is equal to 60 degrees. And so this triangle is equilateral. So that's how we get that this triangle takes up 1/6 of the circle. So with that done, we can finish calculating this. So that's 12 pi times 1/3, which is 4 pi. And so that's the area of the region that is outside of the triangle. And so inside the triangle, we can simply calculate the area of the equilateral triangle by using the side length, which is 12 squared times root 3 over 4, which is 12 times root 3 over 4, which is 3 root 3. So we can now find out the area of this 1/8 portion as 4 pi plus 3 root 3. And if we multiply this by 8, we get 32 pi plus 24 root 3. Um, and then we can add together everything to get a plus b plus c equals 59, which is our answer. Is there any questions? If you have any questions at any point, you can just send it to me in the chat and I'll be able to see it. You can do it either privately or publicly. Both are okay. So in that case, I'm going to assume there's no questions here, and I'm going to move on to the next question, which is number 19. Let me copy number 19 here. Okay. Okay, there. So this is number 19. Um, Number 19 is about is about a game played on a grid that is 1 by 2025. And it's labeled 0 through 2024. And all the scores are initially 0. And then if we have any three adjacent squares, say with values A, with scores A, B, and C, we can add or subtract 1 from each of the scores to get A minus 1, B minus 1, C minus 1, or A plus 1, B plus 1, C plus 1. And so our goal is to reach a place where all the squares are 0, except those labeled 0, 1012, and 2024, which happen to be the first, the middle, and the last square. So we're trying to find out the minimum amount of seconds or the minimum amount of moves Robin can make in order to achieve this condition. So basically the strategy for this is to find a way that minimizes the amount of turns by constructing it sort of And so we can first try to create sort of like a diagram of how our grid will look. So this is our square 0, this is our square 1012, and this is our square 2024. And so all of them are 0 at the start, and our goal is to make this one 1, all the other ones 0, this one 1, and all the other ones 0, and also the last one 1. And so um we can use the symmetry of this situation to make our progress more efficient. So the first move in this case will be getting the 1012 to be a 1. And that's simply achieved by adding 1 to all of these. Sorry, there should be a symbol. And so what this does is it gets our first square at 1012 to be correct. And now we can split this into two halves and do the same thing on both sides. So this will be our first half, and this will be our second half. And we won't touch the middle square again. So what we're going to do is we realize both of these halves have a format where there's a long string of zeros followed by a 1. And we would want to reverse that and get a 1 followed by a long string of zeros. So the general way to do this is sort of to push the 1 backwards. And how we can do that is we can add 1 to the 3 squares before it, and then subtract 1 from these 3 squares. So we sort of move the 1 back 3 squares. And so we can find out that we just made 2 moves, and that moved the 1 3 positions. So this means that in order to get it from 1011 where it currently is to 0 where it wants to be, we need 1011 divided by 3 times 2, which is 674 moves. And so our total amount of moves would be 1 for the initial move plus 674 moves for each side, which is times 2. So that gives us 1,349 moves total. And so that's also how many seconds it takes. So that'd be our answer. Is there any questions for this question? Okay, no questions. Hmm. Okay, anyways. Uh, I'll guess I'll move on to the next question then. So the next question will be number 18. Um, I'll just copy it over right now. Um, so it is this question here. So our question tells us that 3 points are randomly chosen from the perimeter of a pentagon, and we need to find the probability that they form a non-degenerate triangle. So uh let's remember what a non-degenerate triangle is. So a non-degenerate triangle is a triangle that is not degenerate, or a triangle that has a positive area. So if our triangle looks like this, that's non-degenerate, has a positive area. However, if our triangle looked like this, that'd be degenerate since it has no area. And that's what you want to avoid in this question. So now let us draw a pentagon, or let me copy over this pentagon. So here's our pentagon. And so you can see it's regular as the problem states, and all our sides are equal. So we can assume that the probability of choosing a point on each of the sides is equal. So now we will start by using complementary counting. And trying to find the probability that it does form a degenerate triangle. So in that case, without loss of generality, let's say our first point is on this side. it's going to have equal probability of going on any side. So it doesn't really matter and it's symmetrical. So you can just assume it's on this side. It also won't be on a vertex since that has probability of 0. Um, so next we can consider our next point. So if our next point is on the same side, then that's our first step, and our edge looks like this. So in order for this triangle to be degenerate, our last point needs to be on that side too. So our probability would be 1 over 5 for the second point times 1 over 5 for the next point, and this is 1 over 25. If, however, our second point is from another side, like here, and our edge looks like this, um, our next, our last point would have to be one of these 2 points, and that happens to have probability of 0. So this is not a valid case, and you can ignore this. So, that's our probability that, wait, did someone? Um, okay, anyways. So, um, everyone can see what I'm seeing, right? Just to be sure. You see like a pentagon, right? Uh, can someone like tell me that they're seeing like the problem in the pentagon? Okay. Okay, I guess it's working then. Um, okay, that's interesting. Um, so okay, so I'll continue with this. So now that we found the probability that it's degenerate, we can simply subtract 1 from this, subtract it from 1, and find our probability that it's non-degenerate is 24 over 25. And that will be our answer. Um, is there any questions for this? Okay, then I'll assume there's no questions, and we'll move on to the next question, which is problem 17. And let me copy the problem again. Okay, here we go. So this is problem 17. The number is messed up. Anyways, so this question is basically a setup for the Chinese remainder theorem. It's sort of like that. So we see n has a remainder of 3 when it's divisible when it's divided by 5, or 3 mod 5. N has a remainder of 5 when it's divided by 7, or 5 mod 7. And n has a remainder of 15 when divided by 17, or 15 mod 17. And so there's 2 ways to approach this. So the first way is to use a formula and a algorithm to find out, and by considering 2 of them, combining them, then considering the last one. But that is slow and tedious, and it's kind of inefficient. So the second way is to look at the numbers and realize that 3 is 2 less than 5, 5 is 2 less than 7, and 15 is 2 less than 17. So this simplifies down to n is congruent to negative 2 mod 5 times 7 times 17. And this is a unique solution and the solution by Chinese remainder theorem. And so next, all we have to do is to realize the minimum value of n is just simply 5 times 7 times 17 minus 2, which is equal to 593, and that is our answer. Is there any questions for this one? Um, I guess not. So okay. Um, then I'll move on to the next question, which is going to be question 16, I believe. And let me copy over the question real quick. Um, so here's our question. Um, so our question is about the function uh f of x, such that f of x cubed plus 4 is equal to x squared plus 4x plus 4. And so it asks us what is f of 733. So there's again two ways to approach this problem. One of them being to simply try to solve the function and try to find it of x and then plug in 733. But again, that is really tedious and no one wants to do that. So our second way is to sort of fit the 733 into this format here. And so we see 733 is 4 plus 729 is, and this should be motivated by the fact there's a plus 4 here. Um, and so what we can do here is we can notice that 729 is 9 cubed, which is uh not very hard. And then um notice that x in this case is equal to 9. So we can plug x in and get 121 as our answer. Wait, what? Wait, shoot. Is it 100? Yes, 121. Uh, is there any questions for this one, for this problem? Very quiet. Okay. Then I'll assume there's no questions then. Remember that if you have questions at any point, you can just send a message to me or any other of the hosts, and they'd probably answer. Okay, so next question is going to be question 15, I believe. So I'll quickly copy that one over. Um, so triangle ABC has orthocenter H, and so D is the foot of the altitude from B to AC. If the area of AHB to the area of BHC is 1 to 7, find C over DA. And so I hope everyone knows what an orthocenter is, and it's the intersection of the altitudes of a triangle if you don't. So there are basically no properties of an orthocenter you need to know except the definition for this problem. And so what's really useful is a diagram. So let me draw the diagram. Um, anyways, so this is our diagram here, and you can see this is ABH and this is BHC, and so it has a ratio of 1 to 7. Oh, you can't see the question? Let me try to get you to see the question. Um, can everyone see my question now? No? Okay, that is an issue. All the Zoom UI changed, so I don't know how to do anything anymore.
Uh,
Um,
Edward, can you try to let everyone follow you? On
uh,
the top right corner, like there's something you can click.
it says present, but it's not doing anything. And follow my view doesn't work either. Um, no idea what okay. Um, please just go to the top right corner, then click follow me, find my name and then follow me. Um, I guess that's the best we can do for now, until we have a new way. Okay. Um, I see one person's following me.
Can everyone see there's some tab on the top right corner? It says like there is some scroll down menu and click it and shows follow AdWord. Yeah. Can everyone do that? Yeah, AdWord, I can see your problem.
Okay, yeah, everyone should be able to see. I don't know what has happened to, um, I don't know. Oh, you can click follow? What is this crazy
Yeah, I
thing?
believe there's no follow button anymore. And the way to zoom in and out is now to use the plus and minus key apparently.
Um, so I can follow people. Maybe I'm not following. Um, I don't know. It's probably a Zoom bug. I'm on the newer version, so I don't know. Anyways, so please just try to follow me. I'm going to like draw a arrow pointing to where I am right now. So scroll down if you are not here already. How do you scroll? You scroll as if you're scrolling on a web page. Um, oh wait, if you're using a mouse, it might be different. If you're using a mouse, click H on your keyboard and try to click and drag. If you're on iPad, use two fingers. What about a phone? Okay. Um, this is a genuine issue. Where is everyone right now? Let me try to figure out where everyone is looking. Maybe I'll just move to you instead. Um, let's see. Where are you? Following? No. Hey, isn't everyone looking at mine?
Oh wait, actually, I think it would be better if you don't present because once you present, I believe it removes a bunch of options and doesn't allow people to move the screen around anymore.
Oh, how do I not present then?
I think you're no longer presenting because I somehow just got back access to some features. No idea why.
Uh, okay. Try to just follow my feel. Okay, that is working. Um, there we go. Um, yeah, that definitely worked. So everybody is seeing my stuff, right? Right? Everything is fixed, right? Okay, so I think everyone just, oh my God. Can someone else not click that button? It's going to really mess up everything. So don't like click the follow my view button or else that's gonna mess up um something. Anyways, let's continue on this problem now that our tech issues have been addressed. So here's our triangle as again. And so you see it has 1 and 7 as a ratio. And both of these triangles share this base here. And so we just need to compare their altitudes, and that'd be 1 to 7. Fortunately, our altitudes are also on this graph, which are AD and DC, and these are 1 to 7. And so what that means is that AD to DC is 1 to 7. It doesn't really matter what the values are, so I'll just let them be 1 and 7. So now we can find the CA over DA, and that'd be 8. Is there any questions about this? Okay, so I'll assume there's no questions. And I'll just continue on to the next question, which is 14, I believe. Yeah, that's 14. So here is 14. So this is question 14. It asks how many positive integers x does there exist a triangle with altitudes of length 20, 22, and x. So in order to solve this problem, we need to sort of find the relationship between the sides and the altitudes, and then we can use triangle inequality to solve the problem. So first, let's realize that the area is the same. For a fixed triangle, the area is the same no matter what you do to it because it's a triangle. So we can let the area be A. So if the area is A, then our altitudes would be 2A over 20, 2A over 22, and 2A over x. We can simplify this to A over 10, A over 11, and 2, and 2A over x. Um, I'm seeing irrelevant things in the chat. I'm not sure if that's directed towards me or not, but okay, I can scroll. Okay, so we can change this into a ratio, and then the ratio will be 11x to 10x to 220. So because we can scale the triangle and that doesn't affect whether the triangle inequality is true or not, let's just let the sides be 11x, 10x, and 220. So notice here that 11x is greater than 10x. So that means one thing. That means that either 220 is the longest side or 11x is the longest side. So for our first case, let 11x be longer. So in this case, we have the inequality 11x is greater than 220 because 11x is longer. And so x is greater than 20. We also have by the triangle inequality that 11x is greater than 220 plus 10x, which means x is greater than 220. Wait, shoot. Should be a less than sign here and here too. So x is less than 220. Combining this, we get 20 is less than x is less than 220. Let's quickly check that 20 also works. And so let's just put an equal sign here. And ignore this 20 case later. So our next case is that 220 is longer. So obviously in this case, x is less than 20. And 220 is less than 10x plus 11x, which is 21x. So 220 is over 21 is less than x. And so we can combine this with the previous inequality to get 220 over 21 is less than x is less than 20. We also have 20 is less than or equal to x is less than to 220 also works. So any number in the range from 220 over 21 to 220 exclusive work. And so this is equivalent to the range of numbers from 11 to 219. This gives us 209 solutions, which is our answer. Is there any questions about this question? And I hope everyone is still seeing my I'll take that as a no. And I'll move on to the next question. And that'd be question 10. So let me quickly copy over question 10. Um, hmm, let me try again. Um, there we go. Don't know why there's an A there. Why is it doing this? Okay, anyways. So, let's look at this question. It says points D, E, and F lie on sides A, B, B, C, and C, A respectively. And so we have a ratio of 1 to 6 for each of the sides. And we need to find D, E, F for A, B, C. And yeah. So for this one, let's draw a diagram first here. Um, here's a diagram. Uh, it's kind of messy though. Okay, anyways. So this is A, B, C, D, E, F, and their lengths. So it's 1 to 6. And so how we continue from here is we use so there's this formula, there's two ways to go from here. So there's the formula that area equals 1/2 of AB sine C angle C. And there's also a general rule that if we have a triangle here, actually, maybe I draw lines. If we have a triangle here, like this, and we have any other line here, if this ratio here, this to this is equal to A, and this to this is equal to P, then our area ratio of the areas is just A times B. And so either way, these two will lead to the same result, and that is the ability to calculate the area of this shaded triangle I've colored it. And so that area would be equal to 1 over 7 times 6 over 7 of the entire triangle, which is 6 over 49. And in that case, we can multiply by 3 since there's 3 of them to get 18 over 49, and subtract that from 1 to get 31 over 49 is our answer. Is there any questions for this problem? Okay, so I think that's no then. Okay, so yeah, that's it for what I'm doing. Now, if you have any other questions about the problems I did, you can tell me in chat and I'll answer your questions. Otherwise, I think Yichen is talking next.
I start now. Okay, so I'll be going over the next 10 questions from like 23, I guess, to like 29. Because like 21, 22, 30 are like kind of free. So um I'll start with 23. So there we go. Is it blurry or can you guys see it clearly? With the question.
It's
It's
very blurry.
blurry.
Okay, that's weird. I can see pretty clearly. What is this? Bro, what is this? Uh,
I can copy over the question for you if that's an
sure,
issue.
please do.
Question 23, right?
Oh, wait, is it still blurry? Wait, is it still blurry? Or is it better now?
It's still blurry. I'll try
Here,
screenshotting.
23, right?
Oh,
I got it.
Okay, thank you. So for this question, we basically have a right triangle here, like this. and then we have a square here, and this is 6, this is 8. And if we let the side length be x, then we have this is going to be 6 minus x. So we basically just have 6 minus x over x equals 6 over 8. And if you just solve this, I believe that you'll get 24 over 7. Any questions for this? Okay, I'll do 24 now. So, here's 24. Is it blurry or can you guys see it fine?
It's good.
Okay. So for 24, we notice that we have an AB and AB plus A plus B. So you can probably like notice that A plus 1 times B plus 1 is equal to AB plus A plus B plus 1. So if you add 1 to everything here, like A plus 1 here, B plus 1, AB plus AB plus A plus B plus 1, then like you basically get like an invariant, which is basically the product of like all the terms will always stay the same. So then our terms are just going to be like 1, 2, dot, dot, 2022, and then you just count how many factors of 10 are in here of t like totally. So then just use Legendre's formula, which is like the number of factors of 5 in here. So it's just gonna be 404 plus 80 plus 16 plus 3. And you can calculate this out to be 503. And the number of factors of 2 in here is obviously much more. So like there's no point doing it, but like it's like around 2. Like around to 2028, I think, around that. But basically, the answer is just 503. So, like, it's smaller. Okay, and then I'll do 25 next. Can you guys see this clearly?
No, it's not clear. Now it's better.
Right.
Still blurry.
Wait,
Oh, no.
okay. So for 25, it's basically like either we times 2 or we add 1. So, obviously the slowest path is just like adding what like by 1. So this question is basically saying that like we want to find like the fastest way to get to 2023, also the slowest way. So the slowest way is just going to be like going by 1 each time. So like 1 to 2 to 3 to like so on. What are just 2? And this is just going to be 2022 different moves. And if you want the fastest one, then we could just do like like go in reverse. So 2023 is reached by 2022, which is reached by 1011, is reached by 1010, which is reached by 505, which is then reached by 504, which is then reached by 252, then 126. Just backtrack here. 63, so on 62, 31, 30, 15, 14, then 7, then 6, then 3, then 2, then 1. And totally, this is, I believe, 18 steps. Just count it, I believe you can. So just 2022 over 18, which is just going to be 337 over 3, which is the answer of this question. So then I'll move on to question 26. So here, is this clear or blurry? Is this clear or blurry?
It's still blurry. Oh, now it's clear.
So for this, like we can notice that like x minus 1 cubed is going to be x cubed minus 3x squared plus 3x minus 1 here. So here, if you like subtract 1 on both sides here, we get something really similar to that. So it's just xk plus 1 minus 1 equals xk minus 1 cubed. Now, x0 minus 1 is just 2. So basically here what we can do is we just get that x1 minus 1 is just going to be like 2 cubed. And then like we get xk minus 1. It's going to be 2 to the power of just going to be 2 to the power of I believe 3k. So x 100 minus 1 is just going to be 2 to the 300. And if you just take this mod 1000, um, you can use Chinese remainder theorem here, which is CRT. You can like do mod 8, so obviously 0 mod 8, and like mod 125. You'll get that it's 2 mod 125. And this is just going to be 752. And then if you add 1, you get 753, which is the answer. So now the 27. Is this blurry or clear? I'll assume it's clear.
It's clear.
Okay. So if you just count the zeros here, this is going to be 3 to the 16 plus 3 to the 8 plus 1. This is 3 to the 8 plus 3 to the 4 plus 1. So if you just do some division here, you can first like I guess subtract. So you can first subtract like 3 to the 8 here. So minus 3 to the 16 minus 3 to the 12th minus 3 to the 8th. And this is going to be negative 3 to the 12th plus 1. And then you can add back it, so it's minus 3 to the 4th, and then you add back 3 to the 12th, add back 3 to the 8th, add back 3 to the 4th. Then you just get 3 to the 8 plus 3 to the 4 plus 1, which you just add back 1 here. So the quotient is just 3 to the 8th minus 3 to the 4th plus 1. And then this in base 3 is just 2, 2, 2, 2, 0, 0, 0, 1. Base 3, of course. Is this clear? Okay, now I'll do question 28 now. Okay. So for 28, we can like substitute in that x is, I'll call this bracket x plus fractional part of x. So like fractional part of x is just like x minus this like integral part of x. So if you substitute this in, you get that. So x or like whole number part of x times fractional part of y plus whole number part of y, fractional part of x, plus fractional x, fractional y, plus, and then a minus this again, so it just cancels out. And you get that this is just going to be 6, or the like floor of this is 6. And then, which basically means that 6 is less than or equal to whole number part of x, fractional part of y, plus whole number part of y, fractional part of x, plus fractional part of x, fractional part of y is less than 7, like strictly less than 7, by the way. So for this expression, we have to do some casework here. That casework is on whether fractional part of x is less than half or greater than half. So if it's less than half, you can just substitute this in and you basically get that. And if you just substitute like less than half in, you basically get that this thing is just double of this. So it's basically just this times 2, which is either 12 or 13. Because if you like substitute this thing in, you just get that it's 2 times the like whatever that is. So just gonna be 2 times like whole number part of x, y, plus y. So that's 12 or 13 basically. But if x is like fractional part of x is greater than or equal to half, then you can go back here and combine these into just fractional part of x times y. So you basically just get 6 is less than or equal to whole number x fractional y plus fractional x times y less than 7. If x is greater than half, then you just get that 2, like this expression here, it just becomes, is my screen not moving, bro? 2 whole number x plus 1 bracket y plus 2 fractional x minus 1 y. And this expression, you can notice that like there's 2 whole number x times fractional y, then 2 plus 2 fractional x times y, and then it's just the 12 or 13 plus fractional y minus y. So t if you want to find like all possible values, it's just going to be, it's either 12 plus fractional y. Is my Apple pen lagging? Or 13 plus fractional y minus y. And this is just less than or equal to 13 because fractional y is less than or equal to y. So all possible values for this question is just going to be 1, 2, dot, 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 13. And if you sum this up, you get 91. Just the answer. So if there's no questions, I'll move on to the final question, which is 29. So 29. As for the last three digits of this expression, so we can first take 1,000. So of phi of 1,000 is 400. So we can simplify this with Euler's theorem, which basically states that a to the phi of k is equal to 1 mod k. So basically with this 2023 just becomes 23, and this just becomes 723. And now to calculate this, we can just calculate 723 mod 1,000. And then again, we can use Chinese remainder theorem here. So yeah, answer is 366. So if we take mod 125 here, then we can just like bash this out. So we get that 7 is just going to be 7. 7 squared is 49. 7 to the power of 4 is just going to be congruent. It's just going to be congruent to 49 squared binomial theorem. Oh yeah, that works too. So with binomial theorem, I assume that you would just do like 5 plus 2 to 23, right? Is this what you mean by that, Vincent? So that also works, but my method's probably dumber, but also more tedious. So this is just gonna be what? Yeah, this is gonna be 401, and 401 is 26. 7 to the power of 8, you can just keep bashing here. You get that it's 51. And 7 to the 16, you get that it's just going to be 101. So here I actually noticed that you have 26 and a 101, and these somehow multiply up to 2626, which is actually just 1. So 7 to the 20th is just going to be 1 mod 125. So it's just going to be 7 to the 3, which is 343, which is also going to be 93, I believe. And then somehow 7 to the 23 mod 8 is just -1. And then you can combine these two to get that 7 to 23. It's actually just 343 mod 1,000. And if you just add back the 23, you get answer 366. Any questions? Does anyone want to see 30, 21, or 22, or are those just good? Okay, I guess not then. So, and I think now Alex will show you the last 5 questions.
So I think no one wants to see 30 because it's a pretty easy problem. I can move on to later problems. Okay, here. Wait, actually, to be honest, problem 31 is also not too hard. Wait, why can I not move this thing in? Here. So problem 31, in the game, we have 4 colored wires.
Alex, can you please let everyone follow you, please?
So in the game, there are 4 differently colored wires. In order to do this, first of all, we consider, let's say, these 4 wires here, and each of them needs to match to its corresponding one. And since we know that the number of correct combinations or number of correct orderings is just equal to 1, total number of orderings is 4 factorial. So thus our answer for this problem is 1 over 24. Okay, this problem is quite a simple one. Let's move on to the next one. Here. I need to screenshot this. Oh, shoot, I have to move this back. Sorry, give me a moment. Here. So this next problem is an interesting geometry problem. So I'll talk about the way to do it by complementary counting. So the figure itself may look sort of complex. I think the easiest way to do it would be to use complementary. So we notice that there are 3 regions over here, 3 congruent regions, right? So we only need to find the area of one of those congruent regions. That will be enough. Okay. First of all, let's find the area of whole hexagon, the area of the entire hexagon. Everyone knows the formula for the area of a single equilateral triangle, right? For an equilateral triangle of side length s, the area is equal to s squared root 3 over 4. Okay, so the area of the entire hexagon is simply just 6 times of this, and the side length was 6 given in the problem. So 6 times 6 squared root 3 over 4, that is 54 root 3. And now we want to find out the areas of these 3 other regions around here. So in order to find out those areas, let us first cut up each of these regions into 2 smaller parts. So one way we can do that is by connecting Z and D. So once we connect Z and D, you see the 2 different triangles. Let's first find out what triangle EZD is. Triangle EZD's area. Because we have that EZ, that the area of EZ is 1, the area of EF is 6, the length of EF is 6. That's the area of triangle EZD is exactly 1/6 of the area of triangle EFD. And that is 1/6 of 9 root 3. Yes. Okay. All right, and the next part. Right. Okay, so then after that, let's find out the area of triangle ZDY. So the area of triangle ZDY can also be found similarly. If we compare the area of triangle ZDY to the area of triangle EDC. First of all, the area of triangle EDC, that is simply going to be 9 root 3. Then the area of triangle ZDY, so then let's compare the base and height. If we consider this line to be the base, then we notice that the base of dy, the base length is equal to 5, wait, why is that not annotating? Okay, the base length of dy, that's 5/6 of CD. Everyone agrees, right? I just want to make sure, okay. Okay, so then now that we have this, also notice that the height of ZD, let's say if we draw height from Z to dy. So height from Z to dy is 7/6 of the height from E to CD. Okay, so I will quickly explain how I derived this last statement. So first, let's come back to this hexagon. So notice that Z is right here. This is point E, and this is CD. This has length 1, 5, 6. So then clearly, if we compare these two heights, first of all, this length is just 6 times sine 60. Meanwhile, this length is going to be 6 times sine 60 plus this extra 1 times sine 60 equals to, well, 7 times sine 60, right? Okay, so that's why height from Z to dy is 7/6 of the height from E to CD. And as we said earlier, the base dy is 5/6 of the base CD. Then this just tells us that the area of triangle DYZ is equal to 7/6 times 5/6 of the area of triangle CDE. That's 9√3 times 35 over 36. Okay. So that's the complement. The complementary area is going to be 3 times of the triangle EZD plus triangle YZD. EZD plus YZD. EZD plus triangle YZD. And that is 3 times of 3√3 over 2 plus the 35 root 3 over 4. This simplifies to this. And eventually, after we calculate this, we will get that this is 123 root 3 over 4. So thus our area that we want, which is a triangle XYZ, is equal to the total minus complement, which is 54 root 3 minus 123 root 3 over 4 equals to 93 root 3 over 4. And I believe the format that the answer wanted us to give was the sum of A plus B plus C. Thus, our final answer would be 93 plus 3 plus 4 equals to 100. Okay, so that is our method for this problem. To be honest, it's not too hard. You just need to notice, well, that sometimes splitting the area up in like divide and conquer, this strategy is quite effective here because directly calculating the area of ECYD would be sort of challenging. Okay, everyone understands, right? Okay, good, great. Then let's go on to the next problem. Wait, let me first hold this one. So, um, 33. So let's see problem 33. This is another geometry problem. It is more of algebraic geometry, actually. So these are the radii of 3 mutually externally tangent circles. Let's say if these 3 circles have radii A, B, and C. Okay, sorry. Here, great. So now I'm just going to quickly mark out the radii. And it said the problem says that the area of the resulting triangle will be 84. So the area of this triangle, let's first look at the side lengths of the triangle. We know that the area can be determined by the side lengths. The side lengths are A plus B, B plus C, and A plus C. So then we can apply Heron's formula. Why is my pen lagging? Oh. So, but then we apply Heron's formula. Oh my God, it's lagging. Sorry, give me a moment. Okay. Okay, so but we apply Heron's formula here. The semi-perimeter S, that is one half of the sum of the side lengths. The sum of the side lengths is A plus B plus A plus C. Oh my God, my pen cannot. Okay, A plus C plus B plus C. And that is equal to A plus B plus C. Okay, then what this means is that by Heron's formula, square root S times S minus A times S minus, okay, yeah. So square root of A plus B plus C. Okay, A plus B plus C times A plus B plus C minus A minus B, so that's C. A plus B plus C minus B plus C, that's going to be A.
Alex, can you show people the Heron formula in the form of S first? Then you plug in those
For Heron's
side lengths.
formula, yeah, for Heron's formula, if the side lengths are X, Y, and Z, suppose the side lengths are X, Y, Z, and if we define S to be one half of X plus Y plus Z, X plus Y plus Z, then the area, so then what this means is that oh my, cannot. So area, I will just erase that and redraw. Okay. So this means that the area is equal to square root of S times S minus X times S minus Y times S minus Z. Okay, but either way, back to the original problem. Then we get that A plus B plus C times A times B is equal to the area, which is 84. And CAB, this quantity is actually already given to us in the problem. The problem tells us that this quantity is 252. Okay, then what this means is that our final answer is going to, well, actually not final answer yet, but we can first get that A plus B plus C is equal to 84 squared. 84 squared over 252. And this is equal to 28. But then, of course, what we want to do is we want to find the sum of the three side lengths. And the sum of the three side lengths is 2 times A plus B plus C. And 2 times A plus B plus C is equal to 56. So this is our final answer. Oh my God. 56. Yep. So this 56, this is our final answer. Does anyone have any questions on this? No questions? Then we will move on to the next one. How do I scroll out again? Oh, never mind. This is not working now. Yeah. Now let's go back to next problem, problem 34. Okay, so this is an interesting problem that is actually going to be about counting in two different ways. So does everyone know about the way of counting, the method of counting in two ways?
Alex, let everyone follow you, please.
Sorry, I just had to disconnect my pad. It was lagging. Okay, but does everyone know about the method of counting in two ways? How many of you know? Like, raise your hands if you know. No one? Okay. Oh, okay, Vincent knows. Do you know exactly how it's done? Like, if you want, you can quickly talk about your understanding of this. It can be like just really quick, just like a couple sentences about like the rough idea.
So you find two ways to count the same value. You compare those two equations you get from the two ways of counting, and then you like find out the wanted stuff.
Yes. Yes, that is the basically what this is. Wait, let me try to restore the whiteboard. Who closed it? Oh, weird. Wait, that is strange. Sorry, give me a moment. The whiteboard. Can everyone see the whiteboard right now? Or is it like still loading? Here, finally. Great. Okay, so we'll talk about how to apply the counting in two ways method here. Let's first talk about what are the two items that we are going to count. So in our 8x8 grid, stroke thickness. In our 8x8 grid, we want to count the expected number of squares of any size containing a single blue square. So let's first say if this is our blue square, this is blue. Then what we want to count is the number of larger squares, like the number of squares over here, perhaps. And yeah. So then actually, then we can let's write it in sigma notation. Since the expected value in total, it's going to be over all blue squares, which is 64. For each blue square, is this not writing? Oh God. Sorry, give me sorry, my Zoom is having issues with lag. Okay. Oh, that whiteboard quit again. Second time today. And yeah. Okay, so let's continue where we left off. The two objects we're going to count are the small blue square and the large black square, let's say, if we call that like or just larger square containing this blue square. For each blue. Oh, this is annoying. Sorry, technical issues. I think the new Zoom version is strange. Okay, so for each blue square among the 64, we then try to count number of squares, number of larger squares containing it. Okay. Oh yeah, and as Edward said, please do not like randomly draw on the screen. Okay. So then number of larger squares containing it. Oh yeah, Edward, no, I mean Vincent, try refollowing me. So number of larger squares. Oh my God, this is lagging. And also, please do not touch the problems. Whoever is doing that, please do not touch the problems. Okay, so either way, I think you guys get the idea. So basically, we are counting, the first way to count is from each blue square, count the number of larger squares containing it. So then there is a second way of counting. which is also equivalent because in other words, we're just counting the total number of ordered pairs, right? So if we just count for each large square, instead, if we count by number of large squares, for each large square, number of small unit squares contained inside. And so then I think this is a quantity that we can count more easily because for every single large square, the number of small unit squares contained inside is just equivalent to the area of the large square, correct? So then now we just need to sum all of these up. So first of all, how many 8x8 squares are there? If we just first talk about 8x8 large squares, size of large squares. Large squares. 8x8, there's one such square, and this one such square has 8 squared, different small squares inside. If we talk about 7x7 large squares, then there are 2 squared such because there are in total 4 ways to choose 7x7 squares within our grid, and there are 7 squared smaller unit squares within each 7x7. 6x6, this will be 3 squared times 6 squared, all the way till it comes down to 1x1. This will be 8 squared times 1 squared. So thus our final answer will be sum from I equals to 1 to 8, I squared times 9 minus I squared over 64. And at this point, I really don't think there's any other really good method other than directly calculating it. And the final answer here is going to be 123 over 4. And wait, yes, Vincent, I am writing it. It is currently under problem 34. Does it not load for you? Okay. Oh, it's not loading. That is strange. It definitely shows up. Okay, well. Equals to 123 over 4. Wait, how about you guys? It's not loading for you guys either. That's strange. Maybe if it's not loading for you guys either, I might have to send the slides after the meeting.
Alex, let everyone follow you first.
I think everyone is following currently. Pretty much everyone's following. Yes, everyone is already following. Oh, I guess maybe it's like it's just a new version of Zoom. I guess for some people it loads, some people it doesn't load. Oh, that's very weird. Okay. But do any of you have any questions about the double counting?
Alex, can you on the graph, like, because you just describe like, the large size, like 1 times 1's, like, great.
Describe what?
For the question 34.
Yes,
Yeah, can you explain how did you get a 2 square times 7 square and a 3
I
square
already
times?
explained. I already explained earlier.
Yeah, but can you show it on the graph?
I think that is like not necessary. And also, if you so over here, the number of ways to get a 7x7 square. For instance, 7x7 square here or here, or you could have the 7x7 square over here or over here. So that's basically 4 different ways to choose the 7x7 squared. So it's basically because if you think about it, the number of ways to shift the square to the right and number of ways to shift it up and down, there are 2 ways in each direction, so 2 squared. Yeah, okay. But I think everyone understands this one. This should be something that is pretty trivial. Oh, whiteboard is 29,000 random drawings. Yeah, you guys should actually stop drawing. It's making it lag. Okay, then problem 35. Problem 35, it's probably one of the slightly more difficult problems on the test because it involves sort of slightly heavy, maybe, or like if you guys don't notice a couple initial sort of small patterns, then it'll actually be very heavy casework. Okay, but let's first read the problem. We want to find out the number of ways to put 5 or 7 or 9 objects onto the whiteboard such that none of these knights can attack each other. Okay, so first of all, I think one thing you guys should notice is let's first look at this square. Then let's look at this square. at these two squares, I mean. And after that, look at, right. After that, look at this square. So do you guys notice something about these three squares? So notice that if, let's say if you have a knight in this top square, then you could not have a knight in these two middle squares. Similarly, if you have a knight in this bottom square, then you could not have a knight in these two middle squares. And also, if you have a knight in these two middle squares, you cannot have a knight in either of the top or bottom squares. This should be clear because it's just because if there's a knight in either of those positions, you can L shape to other ones. Okay, so but this is the first one. Now I'll go change my color here. And also, whoever is adding a lot of objects to image, please delete all of those. It's creating unnecessary lag. So our second group of squares, we will be looking at this square, these two squares, this other red square, and these two red squares. So notice that if you have anything in the red square in the middle, then you could not have anything else in the red square on the two sides. And also, if you have anything on the red square if you have anything on, like, let's say one of the top two red squares, then you could not have anything in the middle. So it's basically a sort of similar pattern to what we found earlier. Okay, and then let's make one more group of squares. Okay, the whiteboard's lagging too much for me to write. Okay, whoever did all of that, please like remove all of your extra images or whatever.
Hey, hello, everyone. Someone stop, drawing anything over here, okay? We need to quickly finish this problem. Like it's causing an issue here. We cannot see anything. Alex, I cannot see the red square you circled over here.
Oh, that's weird. I cannot do anything on my side currently. It just froze. That's weird. Okay, but meanwhile, while I wait for the lag to get lower, let's first talk about this. So then, and then meanwhile, as for those remaining squares, we will put them into a blue group. And then we will start discussing where we can possibly place the squares. First of all, for the black group, yeah, and actually I am just going to perhaps just stop sharing. Oh, it doesn't even allow me to stop sharing.
Alex, can you start a new whiteboard?
I'm trying to. It's like lagging so heavily I can't close the old whiteboard. Yeah, I'm trying to look at the permissions, how to do that. I already disabled the settings. Hmm. Currently, I think I have the most lag because I'm hosting the whiteboard. Hmm. Okay. But either way, let me find a way to create a new one. Oh, okay. Wait, is anyone else experiencing lag or is it just me? Um,
So you just started a new whiteboard, right?
yes.
Then you copy paste the problem and yeah.
No, I haven't started a new whiteboard yet. It hasn't loaded on my side.
I don't know. I didn't see anything on the screen
Yeah,
anymore.
exactly. Wait, really? Oh well, that's just weird. I'm trying to close the whiteboard. It's lagging very much for me.
It can only be closed by the host. You're the host right now.
I will change you to host. Could you close it? Because I cannot close it on my side.
Now I close it.
Oh, great. I'll create a new white.
Mhm.
What? No, no, it's back, the whiteboard. Could you close the whiteboard again? Um,
Do you need?
Oh wait, okay, whatever. This is just getting annoying. Wait, I'll just close it one more time. Close your question. Send your question. Could you quickly make me host again?
Mm-hmm.
Got it. I'll just have to draw a new graph. Okay. New whiteboard. And everyone, please do not draw on this one this time. I really do not want it to lag again. Here is the image we had. Okay, so let's talk about the groups we were making. We also made another group of reds, this group of red cells. So notice that if you put a knight in the middle red cell, then you cannot possibly have knights on these two sides. And conversely, if you have a knight on, let's say, this side, then you could not have a knight in the middle. Okay, and then we shall make one last group of cells. This last group of cells, I'll color them blue. It will be this, and this. So notice that these group of cells, blue cells are actually symmetric to black cells. They share the same properties as those black cells. If you have anything in the middle, you cannot have things on two sides. If you have something on the two sides, you can't see the thing in the middle. Okay. Okay, I hope you guys can see it now.
Edward cannot see you.
Okay, I think that's
Can anybody else can see the problem, the graph?
Yeah. Okay, so how to place 9 knights? I can see problem. Yeah, and you can see all of those. Okay. Okay, so then let's talk about each of these groups. First of all, let's talk about the blue group. So this blue group how many knights can the blue group hold? And the blue group can hold a maximum of 2 knights. And this can be achieved in 2 ways. Either you use the 2 blue cells on side, or you use the 2 blue cells in the middle. Now let's talk about the red group. The red group looks like this. It's 2, 1, 2. Okay. The red group can hold a maximum of 4 knights. Because the only way to achieve this maximum is to put 2 here, 2 here. And now let's talk about the black group. The black group, as I said earlier, it's just symmetric to blue group. Again, max 2 knights. So then what is the maximum number of knights we can hold? The maximum number of knights we can hold is the total maximum of 8. So the total maximum of 8 knights, basically this means that 9 knights is impossible. In other words, A9 is 0. So A9 is actually sort of the uninteresting, more trivial case. So let's talk about how about A5 and A7 then. So A7 is equal to, well, maximum minus 1. So then in other words, you basically just sort of had to remove 1 knight from the maximum. And okay, so let's talk about how to do this. So originally, so first of all, let's talk about how to make 8 knights. If we first consider the blues, for the blues, you have 2 ways for the blues, because as I said earlier, for the blues, you could have chosen the 2 things on 2 sides or 2 things in the middle. Blacks also have 2 ways to achieve their maximum. And meanwhile, as for the reds, how would you put 4 knights into these red tiles? As I said, only way is to put them on the 2 sides. So for reds, there is only 1 way. But then, as I said, remember, A7 is the maximum minus 1. So we need to find some way to remove 1 single knight. So how many ways are there to remove 1 knight from 8 knights? Well, that's just 8 ways, because you could have chosen any of those 8 knights to remove. So A7 is 2, 2, 8, 32. A9, 0, okay. Now let's talk about A5. So A5, so let's talk about how exactly we split it between the blacks, blues, and reds. Black, blue. Okay, also notice that black and blue are technically interchangeable because they're symmetric. Okay, but either way, I will list these out. 2, 2, 1, like things that sum up to 5. You can have put 2, 2, 1, 2, 1, 2, 2, 0, 3, 1, 1, 3, 1, 1, 3, or 1, 0, 4. Okay, does everyone understand this? Also notice that the blue column cannot exceed 2, the blacks cannot exceed 2, the reds cannot exceed 4, because as I mentioned earlier, there's an upper limit on each of them. Okay, so let's talk about how exactly do we put 2 blacks, 2 blues, and 2 reds. I will first copy this image over to make it easier. So let's talk about how exactly do we put 2 blacks in here? 2 black, 2 blue. So the number of ways to put 2 blacks, well, that's 2. Number of ways to put 2 blues, that's also 2. Number of ways to put 1 red, well, we could have chosen any 5 of these. 2, 1, 2. Okay, over here, as I said earlier, because black and blue are interchangeable, these two technically could be swapped. So I first have to multiply by a factor of 2 here. And then a number of ways to choose 2 black knights, 2. Number of ways to choose 1 blue knight, that would be 4, because I could have chosen any of these 4 cells. And then number of ways to choose the 2 red knights. There are actually 6 ways to choose the 2 red knights. I'm just going to move things here. So if we talk about the number of ways to position those how was it 2 red knights? The number of ways to position 2 red knights, well, clearly we cannot have any red knight in the middle, because if we had a red knight in the middle, it would prevent us from having any red knights on the 2 sides. So thus we can only possibly have 2 red knights distributed among the 4 sides, and that would be 4 choose 2. This case, again, these two can be interchangeable, so I first have to multiply by 2. Number of ways to choose 2 black, same as previous case 2. Number of ways to choose 0 blue, only 1 way because it's 0. Number of ways to choose 3 red, that will have actually 4 ways. This is 4 because, well, you have a couple cases. First of all, you could choose maybe either one thing in the middle and then the 2 things from the sides. Wait, no, not one thing. No, I mean, no, it's just 4 choose 3 actually. Wait, sorry, misspoke. 4 choose 3. Because 3 reds, you could actually not have anything in the middle, because if you had anything in the middle, it would block the things on sides, which would give you at most 1 red knight. So in order to have 3 red knights, the only way is to distribute them among the 4 sides, which would be 4 choose 3. Okay, let's talk about this last one. Number of ways to choose 1 blue and 1 black. That would be 4, because you could choose any of those 4. Number of ways to choose that 3 red, same as previous case, 4 choose 3. So that's 64. I'm just going to quickly write all of these down. This is 96, and that is 20. Okay, final case. Again, interchangeable, so we multiply coefficient of 2. Number of ways to choose 1 blue knight, 4. Number of ways to choose 0 black knights, that would be 1. Number of ways to choose 4 red knights. Now that only has 1 way, because those 4 knights must be the 4 on the sides. That's the only way to achieve that. And this has an 8. We can sum up these values, and we get that this sums to A5 equals to 204. Okay, I will write down our final answer. A5 equals 204, A7 equals 32, A9 equals 0. So A5 plus A7 plus A9 is equal to 236. Okay, so does anyone have any questions about this, or does everyone understand? If anyone has their own methods that they would like to talk about, you're also welcome to talk about your own method of doing casework. No one?
Yeah, I think it's time. It's almost 9 o'clock.
Okay, yeah. Then I think we can conclude the meeting now.
Yeah,
I hope you
we will send the for the students who are not able to come, we will send the recordings to them tonight. Yeah, after I process the video. Yeah. And so thank you so much for Edward and Yichen and Alex to like host this review sessions and like going over all these problems. And also thank you for all all of you guys joining this session. And happy holidays. We will see you guys after January the 4th, right? Yeah, after January 4th. So enjoy your winter break. Yeah,
yeah.
let's call it a day. Yeah,
I hope
okay.
everyone learned these methods and yeah, had a good time learning new methods today. Okay.
Yeah,
Yeah.
okay. Yeah. Bye.